Hello friends, in this quarter of time varying fields we are into the fifth lecture, and here we are going to deal with current and current density continuity equation, which is very important topic, and we shall establish point form of Ohm's law. We shall discuss a numerical to understand the point form of Ohm's law in more detail. Now we have a circuit in which battery is exciting the circuit, and when we place the switch on, the bulb will glow. So in this, current will flow through the circuit, and we define current as rate of flow of charge or other charges. So here we are showing a source in this fashion, and current is moving through the circuit, and in schematic representation we are showing a resistance, load resistance kind of thing, like the bulb we have shown in the earlier diagram. Mathematically, current I is rate of flow of charges. So dq by dt will represent current, and when we are representing alternating current, it is represented by small I and dq by dt. So the flow of charges, and q is function of time. In preceding discussions we are going to handle this as a differential equation of first order. Now charges are measured in coulombs and time we are measuring in seconds. So coulomb per second, 1 coulomb per second can be 1 ampere current. Factually, when we excite a conductor, we have free electrons that will cater conductivity for us. So instead of Q, we have to understand that we have negative charges which will cater conductivity inside the specimen. And when we apply electric field, for example, this end we shall call A, which is excited by positive terminal of the battery, with respect to the end B, the electrons will flow from B to A, while the external current will flow from A to B. This is an important convention one must understand. Now we define a new quantity, current density, that is current per unit cross-sectional area. Obviously, J will be equal to current upon the cross-sectional area. Cross-sectional means the area perpendicular to the motion of charges. The unit of current is ampere, and the unit for area is meter square. Therefore, J, current density, will be measured in ampere per meter square. To make our definition more precise, we define J is equal to di upon ds, where di is a small amount of current flowing through the cross-sectional area ds, and we presume that this ds is small. In more correct mathematical version, when we expand this derivative operator in terms of limit, we consider delta S to be infinitesimal small area, which is a cross-sectional area normal to the motion of charges, and the current, small amount of current delta I is flowing across this infinitesimal small area, and this offers us the definition of density of flux. Now here you can see, as the geometry of the conductor undergoes a change, here the cross-sectional area is larger as compared to the right side end. Therefore, the current density at this end, right end, will be more as compared to the current density at left side end. Now let us presume that I is the current flowing through the conductor, and here this cross-sectional area we have charted with blue color, and the motion of charges is altogether perpendicular to this area. Now out of this, here I am considering small area which is not cross-sectional area, and this area ds bar has direction normal to the surface, and the direction of density of current, or the direction in which charges are flowing to cater conductivity or to make current I flow, is this direction. So theta is the angle between two, and we define di small current. I am just rearranging this equation. Di is equal to j bar dot ds bar. Now this dot product encompasses whether the area is normal or not. In case it is normal, theta will be 0, cosine of 0 will be 1, and will be left with j into ds. But in case this cross-sectional area is not the always case, therefore we can account that particular generalized representation using dot product. And when we want to find complete current through the conductor, I mean to say we are interested in finding current through the whole cross section, then we have to integrate this equation. Integrating on both sides, integration di will be I, and here we have to integrate over j bar dot ds bar. So this integration is rolling over surface, and surface is an entity which is made up of product of two dimensions, and I will be equal to double integration, in fact, which is rolling over entire surface of concern, j bar dot ds bar. Now friends, we are in position to establish the continuity equation, which is very important topic from examination point of view. Let us suppose that we have some region of space under consideration. This blue color region is some voluminous region of space which is surrounded by a closed surface, in fact, and this encloses total charge Q inside it. Now we presume that these charges are shoot out from this region and traveling outside, crossing the surface which is we have considered here. Now these charges are moving. As the charges are moving out, we have current flowing in that particular direction. This establishes some current in the external circuit because of the motion, and we have di small amount of current leaving area ds that makes an angle theta with the direction of flow of the charge. So di small current leaving this small red shaded area is j bar dot ds bar. And in fact, we define current as dq by dt, that is rate of flow of charges. Now, the charge distribution in the region we have considered is supposed defined by a function rho v, that is volume charge density, and the total charge q inside that region can be found by performing triple integral over rho v dv. In case of Cartesian coordinates, you can consider this dv as dx into dy into tz, and the first integration you can consider over x, second over y, and third over z, and so on. The current due to the offshoot of charges I is equal to minus dq by dt. The negative sign here represents the charges are leaving to the closed surface. That convention is encompassed into the negative sign. Now here I want to replace q from the earlier one. So it is minus d dt of triple integral over dv operated on integrand rho v. Now here we can interchange the differentiation and integration operation because they are independent of each other. I mean to say that this triple integral is over space coordinates x, y, z, while the differentiation is over time coordinate, which are not interlinked here. The current, by definition of density of current, we have I equal to double integration over surface j bar dot ds bar. Now in this situation we have considered a region of space where the charges are present, and then we are considering some closed surface which encompasses the volume element. So here double integration is to be performed over closed surface. Now we have two equations. The first one is for I using this, and second one is from another definition of density of current this way. So both are representing the current. So I am equating these two equations. Double integration over closed surface j bar dot ds bar is equal to minus triple integral d dt of rho v. Now here we are going to use Gauss divergence theorem, and we are going to apply the Gauss divergence theorem to this term, left hand side. According to Gauss divergence theorem, double integration over closed surface, any vector field, I am writing d bar and then I have to use it for j bar. D bar dot ds bar is equal to triple integral divergence of d dv. So here we are having double integration over closed surface on left hand side, and on right hand side we have volume integration, and the integrand is divergence of d, that is the degree with which the vector field d bar spreads out. Now we are going to use this for j bar. So triple integration divergence of j dv is equal to minus triple integration d dt of rho v dv. Now you can observe on both sides we have volume integration. So we can differentiate this equation once with respect to x, second time with respect to y, and third time with respect to z on both sides, and we can nullify the effect of this triple integration, and we can rearrange by taking the equation by taking this minus d dt of rho v on left hand side, and we have divergence of j plus time rate of change of the density, volume charge density equal to 0. This is known as the continuity equation. Now quickly we shall go through Ohm's law. I guess everyone studying here has gone through this Ohm's law, but I would like to once revise it quickly. It deals with the relationship between voltage, current, and the resistance, that is opposition to the flow of current offered by the material. This deals with ideal resistance. Practically we do not have ideal resistances, but we are having resistances close to the ideal resistances. This relationship was introduced by a German physicist, George Ohm, and that is why it is known in the literature as Ohm's law. At constant temperature, I am going to define Ohm's law. At constant temperature, the current through an ideal resistor is directly proportional to the voltage applied across the resistor. So here I is directly proportional to V. This can be written as V directly proportional to I, and V is equal to IR. So here we have a triangle representation V equal to IR. In case you like to represent in terms of current, I mean current on left hand side, I is equal to V upon R, or R is equal to V upon I. So this triangle, if you remember, you will not get confused with the order. At constant temperature, the current through an ideal resistor is directly proportional to voltage applied across the resistor. This law also has got some limitations. It is applied to linear devices, some non-linear devices like diode, thyristor, and whenever there is an electric arc, that becomes a non-ohmic behavior. These are the pictures of different resistors, and you can observe some color code representation which determines the value of the resistor, and we remember Ohm's law as V equal to IR for pure resistance. Now if you plot voltage on x-axis and current on y-axis, then V equal to IR, this relationship can be represented by a straight line having slope 1 upon R. If the behavior is not a straight line, then we call that device as a nonlinear device. Now the experimental observations in the laboratory proved that resistance is directly proportional to length of the conductor, and it is inversely proportional to area of cross section. So we can introduce a constant so that we can remove the proportionality sign and write equal to. So R is equal to rho into L upon A, where rho is known as specific resistance, and if we like to define what is specific resistance, we have to take it on left hand side, and on right hand side we'll be left with RA upon L. So resistance is measured in ohms, area in meter square, length in meter, so we are left with the unit ohm. Rho, that is specific resistance, is defined as a reciprocal of specific conductance or conductivity represented by Greek letter sigma. So Ohm's law along with the specific resistance, we can write V equal to I. In place of R we are writing rho L upon A. So V upon L, I am just rearranging the equation, taking L on left hand side, is equal to rho times I upon A. Now here you can identify I upon A is current density and voltage V applied across the length of the conductor will be electric field. So E bar is equal to rho J bar, or J bar is equal to sigma E bar. This is known as a point form of Ohm's law. So here rho is equal to 1 upon sigma is equal to Ra upon L. This quantity is measured in ohm meter, and this quantity one can compare for considering the property of the material. Now here this table depicts the value of resistivity for silver, copper, gold and so on, that may be useful for making some calculations regarding these materials. The specific resistance is the resistance offered by the specimen of unit length and unit cross-sectional area, that is cube. So here we have rho is equal to R. This is the definition of resistivity. The resistivity is nothing but the resistance offered when the cross-sectional area of the specimen is 1 meter square and the length concerned length concerned, L, is also 1. So if we have a cube of 1 meter by 1 meter by 1 meter and we measure resistance across two ends, whatever value we obtained is known as resistivity or specific resistance. In case we cannot have such a big dimension material, then also we can measure resistivity, provided we can calculate the area of cross section and length of the specimen in which conductivity is taking place. This is a dimension independent of this statement is wrong. This is the property that is independent of dimension and therefore known as the bulk property of the material. Now quickly we shall go through an example that will enlighten us some intricacies of the Ohm's law in point form. Let us suppose that an electric field intensity of 0.01 volt per meter exists between 2 points of the conductor of cross-sectional area 10 to the power minus 6 meters square. Calculate the current density and current if resistivity of the material is 1.75 into 10 power minus 8 ohm meters. So current density J will be sigma E, but here we have at our disposal specific resistance, so let us replace sigma by 1 upon rho E and you can substitute the values and calculate the current density. Similarly, the total current flowing through the conductor is J bar dot A bar, which is cross-sectional area, so J into A. So you have to substitute the earlier calculated value of J, that is 57.1 into 10 power 4 multiplied by 10 power minus 6, which is the cross-sectional area, that offers you the value 0.571 ampere current. Thank you.